Today we're going to begin discussing the fundamental theorem of calculus. It doesn't get any bigger than this. It is the single most important theorem of elementary calculus, thanks to Leibniz and Newton. So, here's how it works. The informal version, for any well-behaved function f, meaning it's continuous and differentiable, and any base point a, the area under the curve of f is the antiderivative of f. Good call. So, if f is continuous, and the function g is defined by this, then we know, keep in mind that g is equal to the integral of f of t dt, that the derivative of g is equal to f of x. So essentially, the idea is that this upper limit gets plugged in for t. Now, just learn the skill. It's a hard concept to wrap your head around. We'll talk about it a little bit. Just make sure you're able to do it. So the function g of x is equal to the antiderivative of the function f of t on the interval. So, to go from f to g, it's the antiderivative, but to go from g to f, it's the derivative. G of x is x, the area under the curve. And to go from f to g, we antiderive. Today, we're not going to be doing the whole process. We'll save that for the next video. But we are going to be using FTC1 to find the derivative of a function. We are finding the derivative of an integral. When you think about that, a derivative is a derivative, an integral is an antiderivative, so really these cancel each other out, essentially. What the process looks like is we plug the upper limit in only if the bottom limit is a constant, and sometimes you have to switch where they're at and throw the negative out front to make it a constant, if it's not a constant. But on these examples, most of the time it is. So on this first one, we plug it in. So we get 2 plus x to the 4th, all to the 5th power, but then we plugged in an x. So we need to multiply by x's derivative of 1. So we get 2 plus x to the 4th to the 5th. So it's not too bad when we're plugging in something that has a derivative of 1. Here we're going to plug in the 1, or the u, I'm sorry, the u. So we get 1 over u plus u squared times the derivative of u, which is 1. So 1 over u plus u squared is what the derivative of that function looks like. Now this next one, notice how our constant is at the top. Well, we need it to be at the bottom, so we can flip them, throw a negative out front. Keep your negative when we derive, so the writing doesn't overlap. Negative, plug in your x, sine of x squared, and x's derivative is 1, so it's just negative sine of x squared. Number 4, constants at the bottom, plug the 3x in, so we're going to get sine cubed of 3x, but the derivative of 3x is 3, so this is really 3 sine cubed of 3x. Last one, plug in our 1 over x, so we get 1 over x squared plus 2 times 1 over x minus 1. Well, we have to multiply by the derivative of 1 over x. So 1 over x is x to the negative 1, so it's negative x to the negative 2, or negative 1 over x squared. So that's what we have to multiply by, and we can simplify that a little bit into, remove the negative 1 over x squared out front, becomes 1 over x squared plus 2 over x minus 1. And if I distribute, I get negative 1 over x to the 4th minus 2 over x cubed plus 1 over x squared. And that is the derivative of the integral. This is the process anytime we need to derive an integral. So keep that in mind. That's when we use FGC1. You're going to hear me say 1,000 times between now and the end of the school year, FGC1. And on the AP test, if you use FGC1 and they want you to justify your answer, you can write FGC1. Because justifying your answer means, how do I know I'm right? And you know you're right because of FGC1.